Imagine I have two objects with masses m1 and m2, and the distance between them is r. According to Newton's law of gravitation, which is F is proportional to the product of their masses, and also F is proportional to the inverse of the square of the distance. And also, if I combine these two proportionality, I get this thing, m1 m2 by r squared, which is like multiplying these two quantities. Okay, so the question that I'm going to ask here is that, let's say I have a physical quantity A, which depends on two other physical quantities, B and C. So first I say, of course I get the fact experimentally here, A is proportional to B and A is proportional to C. Then I conclude A is proportional to B times C. My question is, why is B times C? Why is it not another combination like B plus 2C or B plus C only? So that is the question that is the question that we're going to explore more. The answer of which we're going to explore more, of course. So yeah. So as we discussed, A proportional to B and A proportional to C. If A is proportional to B, we can say A equals K1 times B, and in this case, A equals K2 times C. K1 and K2 are constant, of course, but they're a little different type of constant, because we know that A does not only depend on B, or it does not only depend on C, it depends on both B and C, right? So if I'm saying only here that A equals K1 times B, the K1 has to have some sort of value of C inside of it. So I can say that K1 is actually a function of C, because the value of C, it determines this constant K1. Similarly, the value of B, it determines the constant K2. So K2 also is a function of B. Now I can just put the f of C, the value for K1 here, and I can write A equals f of C times B. And in this case, A equals G of B times C, and I'm putting G of B for K2 here. So A equals f of C times B, and A equals G of B times C, where f of C is a function of C, G of B is a function of B, and B or C are the physical quantity B and C. Okay, so f of C times B equals now G of B times C, because they both are equal to A, so they are also equal to each other. And from this thing, I can just take the B to the right side by dividing it, and from I can see from here that f of C equals G of B times C divided by B. So it depends on G of B and the quantity C. And I can say from this thing that f of C is proportional to C, just like I can say f of C is inversely proportional to B. I'm just not going to take this case for B or G of B. I'm just going to consider the relationship between f of C and just my quantity C. So f of C is proportional to C, right? I can see it's linear. So from this thing I can say f of C is equal to another constant K3 times the quantity C. Now I'm actually almost done. I'm just going to put the value of f of C here. So A equals f of C, which is K3 times C. K3 times C times B. So A equals what? If A is proportional to B and A is proportional to C, I can say A is proportional to B times C. Then we can just omit the proportionality and then we can put an equal. Then I have to introduce a constant of proportionality, and that's what we get. So we mathematically actually prove to ourselves it has to be B times C. There is no other option for us. There is no other combination which is justifiable. So that's it. You can actually now, whenever someone says A proportional to B and A is proportional to C, then you can actually No, you can actually have this feeling that it has to be BC because it's mathematically perfect. Okay, that's it.